Hello everyone, I hope you are doing great. Welcome to this tutorial video. In this video, we are going to learn how to model and simulate a lithium-ion battery using COMSOL Multiphysics. We will start by defining the battery geometry and material properties, then set up the electrochemical model and boundary conditions. Finally, we will run the simulation and analyze the battery performance and simulation results. So let's get started. Here we can see electrochemical and thermal characteristics of prismatic lithium-ion battery based on a three-dimensional electrochemical thermal couple model. Before I start the simulation, I just introduce using a COMSOL 6.2, and I use a blank model, and we just review this paper and summarize it, just important equation and modules that may be referred in the paper. Then we will add the features to simulate the exact model. Okay, and also I opened the PowerPoint and I will bring the summarize here. Let me duplicate it. Okay, now just I bring important modeling equation. It is important to read paper carefully and emphasize for yourself and summarize it. But here, just wanted to summarize the equation modules. Okay, let me find here. They said in this work, a simplified three-dimensional electrochemical thermal couple model for 330 Ah ternary cathode prismatic LIB is established on the COMSOL Multiphysics 5.4 simulation platform. Okay, the important is 30 Ah ternary cathode prismatic. Okay, I just highlighted. For each one of them, I can use for a snipping tool. Okay. Here we can choose, and I just a screenshot from the important points. Okay, and excuse me for and three-dimensional. This is also important. Okay. I bring it here. Let's say continue. We continue to find key points. The electrochemical and thermal characteristics of a battery are investigated at different discharge rates and ambient temperature. Okay, maybe electrochemical, thermal. This is it refers to two modules, different discharge rate. Okay, ambient temperature. When the paper said about investigation at uh, blah blah blah, it means that parameters were changed, and these are input of our simulations. The simulation results are verified with experimental result, and the results show a good agreement based on the model. Okay, let me bring these screenshots. And this is so important when you start the simulation. Bring the results of your simulation and compare with the experimental, with similar experiment. And results show a good agreement based on the model and parametric scanning, the effect of discharge rate. It means C, okay, discharge rate C, ambient temperature TAMB, okay, battery aspect ratio, okay, aspect ratio, battery thickness, yes, and heat transfer coefficient H. Okay, on electrochemical characteristic, electrolyte concentration, current density, lithium concentration, normal equivalent stress, and thermal behavior, heat generation rate, temperature, okay, heat generation rate. These are two output of these all of mentioned parameters or variables are output of the simulation, which means electrolyte concentration, current density, Li concentration, normal equivalent stress, heat generation rate, temperature distribution. These are the output of the simulation. The following simulation are simulated and analyzed on the 1D and 3D scales. Okay, it's so weird, 1D and 3D. Okay, the knowledge of this distribution characteristic can help designing and optimizing of large LIVS. Okay, just okay, I bring in PowerPoint and also the last lines, ambient temperature. Okay, this line was missed. Okay, I bring it here. These are very important. I can save it, for example, on desktop. Nice, we continue. Model description and validation. Model development. In this work, 30Ah ternary cathode produced by Jiangsu Clean Energy. This is the company name. is taken as the research target. The battery body consists of a laminated structure of a unit cell, and one unit cell includes positive electrode PE. It is so important. Positive plate, current collector CC. Okay, AL foil double layer with NCM. This is as current collector maybe, and the separator and negative electrode plate CC CU foil double layer with MCB. Okay, here it's seen positive electrode PE. It's divided by current collector AL foil double layer. This current collector, positive electrode, okay, and separator, not referred what is that, but negative electrode is CU foil double layer with MCMB, and another separator. Maybe this is following continue, and this is periodic. This is periodic structure. Separator, positive electrode plate, and then the whole is soaked in the electrolyte as shown in figure 1. Okay. There are 51 layers of positive. Let me screenshot from that. Okay, so I bring it here. It's better use the same size to have consistency. Nice. I continue. There are 51 layers of positive electrode plate and 52 layers negative electrode plate. In total, 102 unit cells are used to fabricate the battery, resulting in battery. It is I don't think that they use 102 for simulation. Maybe some tricky way they use. If we continue, then we will find out how they simulate this high unit cell numbers to fabricate the battery, resulting in a battery thickness of 20.5 millimeter. Okay, including the thickness of battery hard case. Okay, the 3D layered electrochemical model is cooled with 3D thermal. Okay, we have a 3D electrochemical model is coupled with 3D thermal model in COMSOL Multiphysics. To predict the LIV behavior, the explanation for developing model is given below. A containing governing equation, boundary condition, input parameter, the time dependent with initialization study. Okay. Also, we have initialization study. Let me find it. Okay, I'll just Now I continue. The first is electrochemical model. The electrochemical, it's okay. Electrochemical, what I can copy the title. Electrochemical model. I change it as one. I mean the first part. I mean. Okay. The electrochemical model introduced by Newman and his research group. Okay, it must be. We must download it and read it. Is adapted to develop a model which comprises principle of conservation of mass, electron, conservation of charge, and electrochemical kinetics, and it is based on concentrated solution theory and porous electrode theory. Due to the repetition of unit cell, only a simplified 3D layer electrochemical model of a unit cell is developed to reduce computation time, as shown in Fig 1C. It is referred here. The unit cell domain is magnified 600 times in the thickness direction, y direction, to observe variation more conveniently. The domain consists of 5 components. Okay, 5 components. Positive current collector with tab, positive electrode separator, negative electrode, and negative corrector with tab. Okay, and we have 5 components. Let me bring a new one. Okay, we have 5 components for electrochemical model. Okay, I continued. Excuse me. This is the battery schematic. You can see the different unit cell, but here we have one unit cell that is magnified 600 times for finding efficient results comparing to experiment. Here we can see CCAL foil, CCCU foil. Here we have negative electrode separator, okay, and positive electrode. Nice. And we can model it. Let me a screenshot of that. Okay, we can see negative separator. Here we have a tab for negative electrode. These are so challenging, but look at this. Here the tab is the adjunct with the positive electrode, for example, or maybe It is a layer. Yes, as I see, it is Al foil layer, yes. And the positive electrode, this is another layer. Let me numbering that. Okay. Here we have one layer. This is two. First layer, second, third, fourth, and this is fifth. Yes, we have fifth layer or five layer. Okay, we can continue. I continue. The tabs are not coated with the active material and they are not attached. The tabs are not coated with active material and it doesn't matter. The fundamental assumption used in the model are as follows. The fundamental assumption as follows. One, Bolter-Walmer. Okay, the Bolter-Walmer equation. Local current density. Okay. Oh, listen. Let me see that. The active material particles are positive and negative electrodes are spherical and uniformly distributed. Okay. But here I can't see any particle. Maybe just assumption. I don't know. The tree is diffusion, and electron migration phenomena are responsible for lithium cation transportation in the electrolyte. Yes. No occurrence of the side reaction. Okay. 5. The electrolyte transportation phenomena is determined by the concentration solution theory. Okay. Number 6. No change in the battery volume during discharge process. Okay. These are assumptions for the simulation. Number 7. Only solid and liquid phase exists during the working process. Table. Okay. And table 1 lists the governing equation and boundary condition setting of electrochemical model. These are explained in many other literatures. 26 to 32 does not repeat it here. Okay. I hope the reviewer, the author repeat here, but they don't repeat here. It's just a screenshot of this. Nice. I can control map. We can bring it here. Control V. Okay, and we can see table 1, governing equation and boundary condition setting in 3D electrochemical model. Nice. It is help us. It will help us. Let me show new table 1. I just copy that and bring it here. Very nice. These are the clues that will help us get closer to the solution and solve the problem. These are the good clues. Here we can see mass conservation in solid phase, charge conservation in solid phase. Here 2 equation for liquid phase mass conservation and charge conservation in liquid phases. Okay. We have some equations. Okay, we will continue. And maybe later we search the reference of 24, 26. Maybe these are some good clue for finding the best module for applying these equations. Okay, the second part is thermal model. Okay, the second part is thermal model. I bring it here. And call it number 2. Number 2. We highlight it. Okay. Here, a 3D thermal model is developed. This is also 3D. I just highlight this. Using a heat transfer module. Okay, very good. Here, they don't this worst sentence that repeating. And here bring the exact name of module, which is made of the battery core, yes, positive and negative battery tabs, and covered with battery hard case. It means we have a different case look at this. This talk about Fig 2. Here we have Fig 2. We can see the cover of that, the positive, negative tabs are here. And maybe here when we solve this problem, we achieve and we govern the initial values or some variables that can be inserted to this as input values or coupling simultaneously to see the heat transfer, heat distribution, electric field versus capacity, and other properties. Okay. Cover with battery. Then the free tetrahedral method is used for mesh generation. Very good. They talk about mesh generation model. The model and the grid are shown in Fig 2. To simplify the calculations, the thermal model does not consider the laminated structure of the battery core. Okay, it is united as a thermal conductivity and anisotropic material. The model also considered battery hard case. Okay, battery hard case, which is responsible for heat transfer to the surrounding. The energy conservation equation is the governing equation in this model. Okay, the energy conservation equation is the governing equation in this model is rho 0 rho t divided rho t, and okay, Q, it is volumetric heat generation rate. Okay, that is QRE, QOHM, QACT, QEX. And they defined that which thermodynamic consists of the reversible heat, QRev, okay, irreversible heat, QIREV, that is not here, just reversible. The reversible heat is due to change in the entropy of the electrode active material. This is entropy, okay, which is triggered by the intercalation of lithium cations and only occur in porous electrode. Okay, this is for porous electrode. Q reverse, this is in porous electrode. Okay, the irreversible heat involves ohmic heat and polarization heat. Oh yes, here we have a reversible that ohmic and I don't know why they use ACT for polarization heat. ACT, I don't know why. Maybe ACT or action, I don't know. But polarization, maybe they could use the PO or pH, polarization heat. Okay, the transportation of charge in the solid conductor material. Okay, this is in solid conductor, and electrolyte cause ohmic. Okay, maybe the Q act in solid conductor, and electrolyte and ohmic it's in electrolyte. Okay, let's copy all of them. Just use a new. I bring the old. Oh, it's just stored. Okay, nice. I continue. This is the schematic figures, and maybe it's better bring here. Oh, why this is not copy? Control C. Okay, Control V. Nice. I don't know what this conflict. Okay, nice. And finally, we used some arrows to refer what each one of these components are means or meaning. Okay, the polarization heat, it is equal to J lithium T round U divided by round T, and QO is equal to this equation, and Q act is what you see, J lithium, Vs, Vl, and UEQ. Let me just bring all of them. There is a small temperature difference between battery surface and the surrounding, therefore we have neglected radiation heat transfer and consider only heat convection as thermal boundary condition. Okay, as reported by Bahiroy et al., the heat convection boundary condition based on Newton's law cooling of thermal model. Okay, that is number 20. Qx, it's 2h divided by th tm minus t, where the parameter h and th are convection heat transfer coefficient and battery thickness. In the direction of perpendicular to the parallel electrodes, respectively. Okay, the convection heat H can be determined by experimental. Okay, to ensure an appropriate capacity and temperature of the battery, the value of H should not be high. Therefore, in this model, the convection heat transfer consider. Okay, the value are available here. Nice. I just use a new and bring it till there, or maybe you can bring in new page. Nice. And just I copy the highlighted value. I know this value is related to H, heat convection heat transfer coefficient. Okay. Let us continue. Electrochemical thermal coupled model. The average change in the temperature of the battery calculate. Okay, average change in temperature. Thermal model is fed back to the electrochemical model. Okay, fed back to electrochemical model regularly as the discharge proceeds, and some of the temperature dependent parameters change consequently, then sent back to the thermal model to obtain the heat generation rate of a battery. This process is repeated again and again and formed coupling. The 3D electrochemical thermal coupled model is visually shown in Fig 3. Okay. They calculate average change in temperature via thermal model, then coupled to electrochemical model as discharge proceed, and they calculate heat generation rate of the battery. Maybe we need some parameters from the first model and bring it to the second model. We must work on it and think about it. Okay, here I just write the coupling. I write it 1, 2. I mean coupling. Okay. Let me see Fig 3. In Fig 3, we have a 3D electrochemical model that use average heat generated QH, and here average temperature. Okay, average heat generated will go to thermal. Oh, it's so weird. The average temperature, it can. Oh, I understand. The average calculated by thermal model, then fed into the electrochemical model. The heat generated will calculate by electrochemical and back to thermal. This may be continued to have stabilized the result and see the final result. Okay, let me bring this coupling schematic. V. Nice. Okay, coupling, and we have a 1, 2, 3 table that is related to the input parameters. Okay, for thermal, we have density, heat capacity, thermal conductivity. This is for thermal model, and just I copy in the thermal model section. Okay. Nice, we can see the table. This is for thermal, and capacity, initial voltage, and the basic is prismatic battery, initial voltage, nominal voltage. It's maybe for electrochemical. This is maybe a general parameter, and this is for electrochemical. The thickness L, particle radius O, D, 50, D. Okay, we must translate all of them. Let me choose new one, table 3. Okay, I bring it in electrochemical section. New one. Nice. You can see the parameters. Okay. I just continue. This is the basic specifications, and I bring new table. Maybe I don't know why initial voltage, nominal voltage, battery demand, dimension, the wall thickness. I don't know, but I bring it just in here. And also we must find what is the geometry, and this geometry, the thicknesses, the depths, height, and also for this one we must work on it. Okay, let me continue. Let's move on the next part. Model validation. The discharge, performance, and temperature behavior of the battery are used to verify validity of the presented model. Okay. Battery sensor was used and two. Okay. There is nothing important for the simulation. This is just result. And we can leave this section. We can skip this section and go to the next part. Move on to the next part. Here, all the governing equation boundary conditions setting of the present model are solved by finite element method, COMSOL, which is okay. It was repeated sufficiently. The discharge rate, C, ambient temperature, Tm, battery aspect ratio, and heat transfer coefficient played a significant role. It seems these are the initial data for the simulations. I mean, initial variable data that they varied in the specific range, then they see the result. The range, okay, for our studies based on previous study, the effect on some typical electrochemical characteristics and thermal behavior are simulated on 1D and 3D scales. That's so weird. I don't know what does 1D mean here, because we see two part of 3D, but it's so weird for me. Okay. Result and discussion. That's weird. Okay. And now there is nothing more but voltage per. There's nothing more than these are the discharge rate, C. We can see discharge rate, and then they simulate okay. We can bring them also and copy them. Here. Okay. And other data, maybe this is the same. Okay, this is for electrolyte concentration distribution. We can copy that I think this is for electrochemical part. We can bring it in electrochemical part. Okay, this is an electrochemical part, and this is also electrochemical. Okay, so we can copy that. I just resize it. I just resize it and okay, nice. Let me continue. This is heat generation, heat generation versus capacity. And maybe this is from, I don't know, maybe this is from thermal part, because this have temperature rise. And this is from, yes, this is from temperature. And copy that. Okay, excuse me for means I remove this frame and I just resize it. Just change the frame. Okay, these are thermal part. These results related to thermal part, also this voltage, heat generation, electrolyte, and this is this may be from the electrochemical part. Yes, this is for electrochemical part, and I don't bring it. These are for thermal part. Okay. And it's still so weird to me that they said analyze on the 1D. I don't know. Okay, there is nothing more for the simulation, and I can start the simulation. Here maybe for electrochemical part we can just a glance on the ref 24 and 26 maybe, or we can just try to add some some physics and compare the model. Let's bring it from the first. We have this, and now we can work on it. Okay, here I just use COMSOL 6.2. I use Branch model. Here I must add 3D model. In 3D I can define geometry, physics. At first I want to check the physics. Maybe we can add physics. We have many options. For example, we have battery physics. Here we have lithium-ion battery deformed geometry. Also, let me see that I have COMSOL lower. I have COMSOL 5.2. Let me check the equation of 5.2. Maybe some of physics help us. Okay, I choose Balang model. For example, 3D, I just check the physics. And just we can add the physics from add physics. Here I just search battery. We have a lithium-ion battery. Let me add it. Lithium battery with binary electrolyte. Let me add this one also, and lead acid battery. Okay. What is the equation? We can check the equations. Okay, for example, for this one, I just group by a space dimension. I can choose this has electrolyte, and in boundary we can add electrolyte, current density, or electrode surface. Oh yes, I think this is good. Lithium-ion battery, it's good. Let me continue with the COMSOL 6.2, and just we choose LIION, okay, because this is lithium-ion battery, and we just simulate lithium-ion battery. Lithium-ion battery, okay, and I think it help us. It will help us. Maybe. Just let me continue. Just wait. Okay. Here we add a lithium-ion battery, LiO. Okay, I can choose, for example, I choose a space group, a space by dimension. Okay. I just group by space dimension. And here we have many properties that we must check all of them. Okay, but I don't change any options. I just continue to find a better okay. Here, before checking the equations, I just recheck the geometry for this equation. Maybe is similar to let me check electrochemical model. Here we have rho CS, rho T, ds Let me check this option: mass conservation in solids. For example, this is separator. In separator, we have divergence of JL, it's equal to RL, IL is equal to QL, and this was for separator. It means in solid phase, in liquid phase maybe. We have some different notation, but let me write this and compare it. Here we have let me write it. We have mass conservation, the equation number 1. It's rho CS rho T equal to ds rho 2 CS rho R2 plus 2 divided by R rho CS divided by rho R. Mass conservation in solid phase. Let me check the solid phase. You can add electrolyte, separator, or porous electrode. We can add 2 porous electrode, porous electrode 1 and porous electrode 2. Okay. And the separator as electrolyte. Okay. Here we have a solid phase. It means we have mass and charge. We check all of them. This is a mass for solid. It means we have a porous electrode. Yes, we have a porous electrode. Let's check we have porous electrode, and we want to write mass conservation for solids. Rho CS rho T, and this is because we don't have time here. I just add arbitrary time in a study. I add a study, time dependent study. Okay. In the time dependent, I add it. Okay, just by double clicking. Excuse me. Okay. Now I go back to porous electrode. I just check the time dependent. You can see the new term. Very good. We have electrode volume fraction and electrolyte volume fraction. Okay, very good. I will check everything. That is the exact module or not exact modules. We have activity dependent, transport number. Okay, electric self diffusivity. Okay, we will check all of them. Okay, you can see in COMSOL we have rho epsilon 1 C1 divided by rho T plus divergence of J1 equal to R1. And JL is equal to this. It is so hard, but what is the new Li? Okay. Oh, nice. Here we have many many parameters, many variables, and here we have particle in intercalation that I saw it in the paper, and let me show you particle intercalation. I saw that. This is particle surface distance, and this is species concentration, particle size. Okay, heat of mixing. Okay, calculate stress and strain. Nice. We can find all of them, and also here we have Balter-Walmer lithium insertion. Oh, very good, very good. We will find it. Okay, I go back here in the. Okay, let me check all of them. Nice. We have Balter-Walmer define local reaction current density. Balter-Walmer. Where is it? Balter-Walmer. Here we have Balter-Walmer that asks us exchange current density. The default was lithium insertion. Well, when you use this lithium insertion, we need this parameter, but the paper talk about Balter-Walmer. And we need the exchange current density, analytic transfer, catalytic transfer, and we leave it as a default. And although we can use a limit current density, but just I leave it as default. Also for this one, I choose Balter-Walmer. Nice. I continue. The active material particles of positive and negative electrons are spherical and uniformly distributed. Okay, this is a spherical. This is a sphere type. Okay, and for this one, this is a sphere. Okay, and we have a table. Let me check the particle. The thickness is 62.7 micrometer. Doesn't matter here. Particle size at D50. I don't know what is D50, D2R. I don't know what this means. I understand it. D, it means diameter. Yes, diameter, and R is radius. The radius is 5 micrometer for cathode. Let me change this porous electrode as, for example, change it as cathode. Okay, and this one as anode. Nice. Continue. As anode. Okay. And the particle for cathode is R is 5 micrometer, and for anode is 7. 5, that is 7. This is 5 micrometer. It's E minus 6 meter. Okay. 5, that is 7. Nice. And we can leave all of them and just check the other result. Let me continue. Initial capacity. This is solid phase, and this hint us it guided us to the solution. For example, solid phase volume and electrolyte volume. Solid phase volume fraction is, this is we are in correct position because solid phase in cathode and anode, and separator is electrolyte. And let me choose electrolyte. Separator is a name. Separator, okay, and we write it electrolyte. Nice, electrolyte. And it's better we have okay, we have, for example, for the electrolyte you can see the here the electric volume fraction is 0.43. This is electric volume fraction. Nice. And other properties, I don't know, we must check all of them. In material, maybe we must add maybe blank material, one, duplicate, and also maybe we can search in library. Okay, but let me choose arbitrary, duplicate. I add this as cathode. This one as separator. Separator, and the second as on. Nice. We have these three material. And now we continue. Cathode, separator, anode, and okay. Now we can trust this equation, and just I write it here. We can maybe recheck it again. Just let me rewrite it again. And these are, you can see the all of parameter, for example, total number of unit cell, Faraday constant. These are not so important. Or transferring number of lithium T plus. Let me see. Transferring number of lithium transfer. I saw that. Yes, T plus. Transport number we can use for material. We must add it here, but after drawing the geometry, we define every of this material to the specific geometry. Then we can add from material and define the values. Here we can see this is 0.36 just for separator. Let me see that. But we have it for electrode porous material also. Let me check. And also we have it for electrolyte. It's so weird. I don't know why. Because we have transport number here, and also here we have transport number. And in table, it just refer to separator. Maybe we can use 0 for them. Let me think about it. I must think about it. I don't know. Maybe it will disable. Sometimes when we add material, it will disable. Yeah, maybe it is calculated by the equations, because we have porous electrode reaction and we have a stoichiometric coefficient, and it will it will define by this stoichiometric coefficient. Okay, I understand. And this is why it doesn't define it, but it will define automatically. And also we have seen a store. Look at this, is data provided by the battery manufacturer, and is data directly used or adjusted from the available data in the literature. Okay. We have a reaction rate coefficient. Reaction rate, let me see that. Number of elements, element order. Okay. I don't know. Reaction rate. What is material reaction rate for just cathode and anode, not separator? Reaction rate coefficient. And I can save it. Let me save it. This PC, desktop, save. Okay. Reaction rate. And we have seen intercalating particle. It was on the paper properties. Electrolytic conductivity, diffusivity, transport number, okay. Activity. Maybe this is, let me use user defined, no. And what is the unit? Met per second, okay. Met per second, meter per second. Let me see that, met per second. Nothing here, nothing there. Particle. We have initial species concentration and initial electron concentration here not provided. I don't know why, but it must have values. We have, let me check porous reaction. Here we have exchange current density, anodic transfer coefficient, okay. So this must be Walter-Wallmer, which is so weird. Nernst equation. I don't know, it must work on it. Equilibrium potential, maybe. Check the electrolyte. What was that? Equilibrium potential. Nothing here. Nothing here. And initial voltage, maybe this is, I don't know. I really don't know. Okay. What is that? We continue. What is that? I don't know. It's particle base, exchange current density, XPR. Okay, here we can check the other parameters. Reaction rate coefficient, I can see here reaction rate. If we choose, for example, lithium insertion, no, there is no reaction rate constant. Oh, if we choose a lithium insertion, we can see the rate constant. But what is Balter-Walmer? I don't know. Okay, here reaction rate coefficient. Okay, electron area density, electrode solid content, initial capacity. We have rate constant. If we use linearized anode, nothing. Cathodic, nothing. Thermodynamic, nothing. And maybe we must choose a lithium insertion. We can see the same equation. If we choose, I choose a Balter-Walmer, look at this, the equation is still the same. I0, alpha A, alpha C, alpha A, alpha C, and electrolytic. It is the same, you know. Maybe this is the Walter Balmer plus rate constant. Maybe we can choose the rate constant here. This is 83 e minus 10. 10. It's for cathode, and for anode it is okay. This is for anode. It is 88 e minus 10. Okay, let me continue. Electrode area density. Electrode area density, what we can see. We have SOC, I don't know. And also we may add a cross electrode reaction that we have on it, or double layer capacitance. If we add it, we have double layer capacitance. Let me see what electrode initial capacity. Maybe this is important, I don't know. You can add it, just this is arbitrary, okay? I can add for both of them and just use the arbitrary value, but it is so important that changes, and I choose particle base. Okay, I don't know where is the electrode area density. It is area density. Let me find it. Oh, I don't know where is it. It's maybe. Let me find it. If we choose it user defined, the unit is 1. Look at this. And we have initial species concentration. Okay. Equation. Oh, this is the equation. Maybe I saw it. Let me. Maybe this is rho CS rho R is equal to 0. It is equal to 0. Okay. This is rho CS rho T. Rho CS rho T and equal to divergence of ds gradient cs. Let me rewrite it. This is paper and this is COMSOL rho cs rho t. This is the same, you can see that, but the right part is divergence of ds gradient of cs. We can bring this is because constant value, it can we bring out from the parentheses. We can write ds divergence of gradient cs. It will be equal to ds. ds is the same as ds here, and this is del 2 of cs, that if we open it in the 3D, it has I don't know why it right like here, it in 3D it may be difference Laplacian. I mean Laplacian, and in 3D if you open it in Cartesian, it will be rho 2 rho x2 plus rho c2. For 3D we can write rho 2 rho x2 plus rho 2 rho y2 cs rho 2 rho z2 cs. But if we open it in for spherical, call it the Laplacian, excuse me, will be for a spherical, it's equal to 1 R2 R2 rho CS rho R plus one R2 sine theta rho theta sine theta CS rho theta plus 1 R2 sine theta rho 2 CS rho phi 2. Okay, it will be for 3D spherical, excuse me, it's for spherical. And if we consider some symmetry, I don't know, the paper said that it must be just R2. If just consider the first term, we will have R2, this integration it will be 2R rho CS rho R plus 1 R2 rho 2 CS rho R2. And here it will be 2R rho CS rho R plus rho 2 CS rho R2. If we consider the first term, we will see it is rho 2 rho R2 rho 2 rho R2 it's the same, and also 2R rho CSR, let me see, and this is, and we have DS, but I don't know why the second term and the third term ignored. Why? I don't know. Maybe we can conclude that CS, it depends only the radial coordinates. If our CS, it was R dependent, not CS, R and theta and phi. Okay, if our CS was dependent to R, these two terms will be 0. Okay, it's because it's depend to the the radius, and it means we have a spherical symmetry. The concentration is the same at all points that are at the same distance from the center, and it will be valid for CSR, not valid for CSR theta phi. Okay, and it's okay, we just define CS just for R theta phi, you know, and okay, we can continue. And this is valid. The module we used, it seems correct. The module is correct, and we can continue. Okay. Now I continue. This is the correct module because we approved this equation. We have derived this equation, and we can continue. And each one of that was valid. I just used a sign to remind myself that is checked. Okay, for example, this was checked, and I choose it. This was checked also, and this is for mass conservation. The mass conservation in liquid phase. Let me check the liquid phase. This is electrolyte, that is a liquid phase. How we can see ρ C, we have the ρ divided by ρ T, divergence of J. If I write the J d gradient C, it means Laplacian of C, and the same result, but we have a new term of ILT plus F. IL, this is the Ln. Let me check. This is the same epsilon, yes. Laplacian of gradient C plus T 1 minus T divided by F. 1 minus T, I don't know where is 1 minus T divided by F. It means F must be the reverse of this. Let me check the F. Where is the F? And just they don't talk about F, or excuse me, we have JLI. Okay, JLI, JL, we can write it as JLI. Yes, that is divided by F, and IL is equal to this, and it is okay. I think this is okay. IL is equal to this. They talk about IL. Where is IL? Here maybe. They talk about charge conservation, gradient, JLI. Yes, it is here. JLI. But here we have IL. We can also see here maybe it is sigma L, gradient phi L, gradient phi L. We can see a 2RT divided by F, 2RT divided by F. But we have sigma. What is sigma here? But we can see sigma. Oh, it used a co-effective in back of the brackets, and lnf lnc 1 plus lnf lnc 1 minus t plus 1 minus t plus gradient cl divided by cl, gradient lncl. Oh, maybe, I don't know, maybe some gradient lnc. It seems the paper in somewhere was wrong. And also if we choose gradient lnc, it means gradient c divided by c. It is the same. Gradient of ln let me check it. Oh, let me check. I will write it here. We have let me check the COMSOL. We have gradient of ln c cl. That is, we can gradient of ln is equal to gradient of cl divided by cl. It is correct. Yes, it is correct. Yes, the notation is correct, and the formula are valid. And this is a valid charge conservation in liquid phase. In electrolyte phase, we can see that. Nice. Let me continue. This was valid. I insert shape on it. Another time and this also. And let's check the mass conservation in a liquid phase. And also this was valid. This is mass. This is mass conservation law. And also for this, here we have it. Yes, we check all of that, and these are valid also. 1 minus t for liquid phase, that is electrolyte. 1 minus t, and this is here and valid. Let me bring it the shapes, and this was valid. but I don't know. This valid, yes. And here rho CLX equal to 0. Let me check. It must be in flux, maybe. This is these are, yes, these are valid. Okay, here, and the J and the JL rho C rho X. Let me check it. Okay, charge conservation in solid phase. JLI is sigma F. In porous, we have JL, CL. It is the same as electrolyte. We have T also, but T won't consider a material. Okay, and this term will diminish, and we have sigma L gradient of phi, sigma L gradient of phi, excuse me, sigma L gradient of phi, and we have a gradient, another gradient. Divergence of JL, sigma L, it means Laplacian of phi L. Laplacian of phi L, yes, it is the same. I choose a shape here, and this is, and it talks about phi cc at x is L, it's equal to 0. I don't want to talk about these are boundary condition. Okay, governor equation and boundary conditions. These are boundary condition, and the boundary condition are in boundaries. Okay, I don't want to talk about here because we can add, for example, electric surface, and we add external electric field as 0. Okay, it means we have phi cc 0, and now I just remove it. For solid phase, it means cathode and anode. Or we can add the current. Let me show you how we can add current. We can add electrode surface, and we can add electrolyte, for example, electrode current or current density. Okay, let me check what is that. This is, and we can check the current density or current. We can both of them. It doesn't matter. Let me check. That is current or current density. I don't know, but we can change it. I add electrode phase to current or current density. If I add current density, it must be, and we can invert electrical, and I add the current density here. Maybe in table, I don't know. In a general table, capacity, initial voltages, nominal voltages, not here also. Okay, we can continue. Okay, and here the geometry domain we can see here: electrode width, electrode height, and what is the electrode depth? I don't know. Width is provided by the battery manufacturer. Width, height, I don't know. Electrochemical. It was electrochemical. It means if we add height, width, depth, and as you can see, these are not the same. These are not the same as I see. And also here, these and these rectangular, not square. Okay, let the plot geometry, electrode width, and also we check all of them: electrode area density, electrocyte content. We will check all of them. Okay, but now let us continue with the parameters that we can define it. Width and height, 97 millimeter, and also we have thickness, that is micrometer. It is so weird. Oh, maybe these are, yes, these are the cathode and anode. That is so thin layer. Okay, we check it now. And also I forgot to talk about we have round phi, round x. I don't know what is that. Okay, but we'll investigate that. Here we have electrochemical kinetics, JLI, alpha, gamma, I0. Let me check this part. Here we have porous electrode reaction. We have the same equation: I0, AXP, alpha, A, F, eta. We have C, the same equation. If we choose limiting current, it must be, we have ILOC, but we don't see ILOC. Okay. And I0 is equal FKCS, CS max, CS alpha, and we have here. Okay, let me just mention it. We bring this and we bring this. What about eta? Where is the eta? Limiting current density. No, it must be not checkbox tick. We can uncheck this box or untick this box. This box, I mean. Oh, okay, but we forgot to. Eta is phi s phi l. Eta, where is eta? Not provided here. Maybe in equation. Yes, in equation we can see eta is ECT equal. ECT is phi s phi l EQ. Phi s phi l EQ. Okay, EQ here UEQ. It is the same. Okay, but the notation is different. And just we must bring these boundary conditions, and the module is correct. The module is correct, and just we must add the boundary condition. And also we will bring this condition here, and also we bring this condition. Let me check this. We bring the current density, that is n dot is it's equal to ins ins is equal to rho cs rho r. I don't know, but it must be the same because we have the current, and it must be the I ds rho c rho r. Here ds rho c rho r equal to j. Yes, it is equal to j, and j it will be n dot jl or is. Yes, why it is is? Because this is for solid. Oh, I understand it now. There we have is and il. Let me tell you what is we have. Look at this equation. We have il and is. It means we have a liquid, S is solid, it for cathode, anode, and it is for separator or electrolyte. Okay, and when we talk about the il, it means, look at this, we have il, this is for liquid, these are for liquids. When we talk about is, it is for a solid, and this is valid for solid, this is valid for liquid, and the T, it's valid for liquid. Okay, it is correct that we see L here and pros electrode, but we have a cathode that is solid and it will be available. But here for electrical material, it will be calculated by IL. But here we have porous electrode. Just for domain material, we can't use separator for electrolyte. Okay, because we have electrolyte properties that is coupled with the porous electrode. Okay, I hope you understand. It is so easy. L is for liquid. That liquid is separator or electrolyte, and S is for solid or for cathode and anodes. Okay, just this. And IL, it's just for L, it's just for S, and IL, it's just for L and it's for S. And here we can see this is Cl, that is for liquid. Okay, this is for liquid, and because the all concentration and events and chemical reaction will occur in the electrolyte, and you can see Cl. You can see Cl. But we can write also C for Cs. It means for solid phase also, cathode and anode. Okay. I can continue. Here there are many equations. Okay, here I choose a liquid electrolyte. Let me check also this assumption. If I choose a ion conductor, the equation not the same, and I choose liquid electrolyte. Okay, we can choose a cell state of charge, but it is not mentioned in the paper, and I just uncheck or untick this box. Okay, we can continue. And here for charge conservation in solid, we can see rond phi, rond x. We see current, we have current, but it is not current density. Maybe we can add, we can see I thought, let me see, where is the I thought? ITOT, nothing there. Maybe we can relate it to capacity, maybe. I don't know. Maybe we can relate it to capacity. I must think about it. Oh, this is maybe discharge current. Oh, and let me check the capacity. Just I'm thinking about it. Excuse me for a delay. I'm really thinking. We can define cell capacity by ampere hour cell capacity ampere AH. Let me define this equation, maybe help us. I define, for example, capacity C by the initial value was 30 AH, 30 AH, mass multiplied to H, and we call it cell capacity. Okay, and now we can define I0, or maybe I see that is equal to capacity divided by 1 hour and also we can also divide this value to area. It doesn't matter, because it's, or I can define JC, that is equal to IC divided by area, and I defined area, that is width to depth. And here I define them. Let me define them. I don't know what is the dimension. It means 100, 139, 20.5, the wall thickness. It's really, I don't know. But here we have a table that I can bring here. Okay, we have thickness for cathode, anode. The separator is so thin. So weird. Really, I don't know. Continue, and this is 100, 139, 139. What it means? 129. Here it's 100, 139. I really don't know. 100. This is talk about cathode high, and it's about 129. Or maybe it is electrode width, electrode height. Oh, okay. Yeah, it's okay. Electrode cell capacity per H. Oh, we will correct it. Just electrode width, electrode height. Say 129, maybe at 10 millimeter. Due to this, it's separator. Yes, maybe here we have 97 electrode widths for cathode. $100 for other. It's so weird. And here talked about electrode height 129. Uh, 97. The width is the same, maybe, I don't know, but I see empty geometry. Let me see this. No, these are not empty. We have this 97, height 129. This is for electrochemical, and this is electrochemical, okay? And 97 for width, height 129. I don't know, really, I don't know. We have positive electrode, separator, negative electrode. Okay. We have negative, positive, separator, and foil, Al foil. In simulation, we can see these are halo. Yes, I understand it. Okay. I understand that. Negative electrode. Negative electrode, it means anode, it means cut. Positive, it means cathode. because here also, let me see that positive electrode Al, negative electrode Cu foil. This author, so weird to me because they talk about positive, negative, anode, cathode. It's the same. Why, I don't know why. Here they talk about Al foil cathode, separator anode, Cu. Cu is anode, Cu is anode, Al is cathode. Yes, positive is cathode. I was right. Cu is anode, negative electrode. Okay. We can plot it. Just let me think about it. It must be very low. Okay, the width must be 97. 97 width. The height. Oh, why I see that like. This is height. The height is 129 for electrode. These are electrode 129. But here it is 139. It means it is 10. Yes, I understand. The total height is it must be 10. Okay, let me analyze it. Ctrl C. Okay, I just crop it. Okay. I add text box. It must be 10 millimeter. It must be 129 millimeter. $129 millimeter. Yes. And this is maybe like square, I don't know. It is like a square. Oh, really, I don't know. The width. Electrode width 97. Um, threshold is 97. It must be this. I don't know. 97, 97, 100. If we assume that is a circle, excuse me, this is a square. This is 97 to 97. I don't know. Width 97 millimeter. Depth 7 millimeter. And the height was 139 or 129 millimeter. Okay, we can choose a block width depth and height. Okay, maybe the same, I don't know. And we must cut it to 1, 2, 3, 4, 5 layers. Let's divide it into 5 layers. Divide it. Okay. Let's divide it to 5 layers. And what is the height of them? It will be challenging, maybe. We have thickness, that is micrometer. Maybe it must be millimeter, I don't know, 62, 20. And oh, I remember that. They told about 600 times magnifying. Let me see that. They talk about magnifying 600 times. Yes, here 600 times thickness is magnified. It must be multiplied to 600. Maybe. Let me just copy that in the y direction. Okay. If I bring it here, the secret of the paper will be revealed. Every paper is like a secret, and we must find that clues to find and revealed the secret of that. 600 times, it means it must multiply to 600. And let me insert text box. Must be multiplied to 600. Is 600, and we can do it by calculator. Okay, 6.27 to 600. Okay, and if we divide to 1000, it will be 37.62 millimeter. L cathode, millimeter, and plus me. Nice. And the next one is L anode. It's 84.5 divided by 600 is 50. Okay, and the last one is separator. It is 12. It's 12 millimeter. If we, this is 1, 2, 3 layer, it must be others. I don't know why, but let me sum these values. L tot is L cathode plus L anode plus L separator. It's about 100 millimeter. Am I right? If added, yes, it's about 100 millimeter. 100 millimeter. It is the same or not? This is 100. Here it must be the L is thickness, yeah? The L is the thickness, yes. The thickness, it means in this position, and it is 100, and this is 100, maybe 100. L total, maybe. And also we have two other layers, this one and that one. That must be, when we see this value, it must be cathode must be lower than anode. Cathode must be lower or thinner. Here cathode it's bottom, anode is top, and anode is bigger. Anode is bigger, and it is here in this cathode separator. Yes, and this must be when we add this is about 100, and it must be about 1 millimeter, 2 millimeter, I don't know. Really, I don't know. Wall thickness, it's about 100 here, but 100, 139. What is 25? It may be for this. 139, 25, 25. This is 100, 139, 29. It may be for this. Yeah. But for this, it must be different. The width 97. Electrode width, electrode high 129. It's okay. It's 97. It's about 3 millimeter. As I see, electrode width it's 62, 84. I don't know. When we multiplied them, cathode and anode, it's about 87. Separator is about 12. It's about 100 millimeter. I really don't know why this paper so weird, but it doesn't matter. We choose for example, if we choose 97 electrode high one, it is 10 millimeter. If maybe 2 millimeter, maybe. We can choose, for example, 2 or 3 millimeter. L, CU and AL. If I write AL for cathode, and Cu for anode. LAL. C for cathode. For example, 3 millimeter. L Cu for anode, 3 millimeter. And we can choose H tab. If I write, what is that? That was tab, excuse me. You can choose Cu foil, Al foil, okay. No, it is good. Tab 10 millimeter. Okay. Now the height 129. That is doesn't matter, this 129 is okay, but we can add H tab. H0 plus we can add it as H tab, okay, in different position. Okay, L cathode, we can cut it from the right to left, okay. You can cut it from right to left and consider L total is must be L tot plus this plus CUA, and it must be the, I think it must be the depths. Let me check it. Yes, it must be the depths, because you can see this is the depths. X, Y, Z is the same, yes. Okay, this must be depths, and I can choose depths as this value and write depths instead of that. Okay, here we can choose layers that we write here. I bring it in the layers. I add the layers from L cathode, we want from start from the back, that is cathode, positive electrode or cathode, okay. I just cut it this. I talk about the layers adding that as I told in previous videos. When we have the n layer, we must add n-1 layer name, and cathode, it must be cathode here. Okay, it must be separator. Nice. Must be anode. And we can from write we have, I don't know why the right will be here. Why it is layer number 4. Okay, L anode. We have 5 layers: CUA, cathode, separator, anode. What is problem? I don't know. From the right, from the left. Or maybe it must be from front. Must be from front. Nice. And now we can see this is the first maybe is cathode positive. I mean, this is a AL foil or AL tab, and positive separator and negative. Nice. This is now it's correct. Okay. This is our layers, and we add it. Now we can add also AL foil. I can duplicate it as CU foil. Okay, and also we can add 2 tabs. Tab 1, 2, doesn't matter, maybe here and here. Let me see the result. Okay, it doesn't matter. Where is it? Where is the position? Just I add them with H tab. I can add another block. I will duplicate it, but I remove the layers. Instead of etched height, I choose, excuse me. Here, I forgot to remove. I must add the H tab in block 2 as high. Okay. It must be H tab. It must be. Oh, I forgot that the H in the Z direction. Yes, the H. The H it's bigger than. For example, it is about maybe 10 millimeter, but the depths the same, but the width lower. Width, for example, width 5. H tab maybe 5, and the direction must be from Z is equal to high. Okay, it must be depth to 5. The width must be the same as LCU widths and depths. Widths, no, excuse me, it must be depths, and it can be widths 5 times. Okay, and we can bring it in the middle, for example, x width 3. Okay, and the height also, it can be 2 times. Okay, and I can duplicate this block. I rename it as AL tab or foil. It's better foil. Foil. This is CU foil. In the top of here, it may be the position Y must be depths minus L CU or AL. Oh, excuse me, it must be AL foil must be CU. Okay, it must be L minus LAL. We can bring it to the right. Okay, it is maybe the same. Nice. And now we define all of them. For example, CU in beside of cathode, CU cathode separator anode AF. Okay, this is CU foil, this is AL foil, this is anode, excuse me, this is CU foil, this is anode or negative, and this is separator, and this is cathode, and this is CU foil. Okay, all of that are defined now. For lithium-ion battery, we don't need this foil, just for showing, you know, it is just for showing the total geometry. And now I can add okay, now I must in lithium ion I just must add the data here. Look at this. For example, in separator We need diffusion coefficient, transport number for anode, for cathode. Here we must define electrolyte. Here I just add anode was here, and cathode was here, and the electrode is the middle. Now in cathode, this is cathode, and we can see transport number, activity dependence. For anode also, and for separator. Maybe porous matrix, they don't talk about electric double layer capacitance. I didn't see the data. But I see Faraday constant. Maybe we can, for now, we can disable it because we don't need it now. Or we can remain it, okay? But there is no data that insert for this. Okay. Now I need the other data. And also I forgot for porous electrode, here we must add electrolyte material. Here we have separator, and also for this one we must add the electrolyte material as separator. Okay, now in separator we have transport number, and you can't see transport number anymore. Look at this, there is no transport number, just for a separator, because it is important to use separator electrode material for both electrode, cathode and anode. Okay, it is for that. And just okay, now I must add the values. For example, diffusion coefficient for cathode, just let me check it. Diffusion coefficient. Okay, I continue. Here Oh, excuse me, it must be there. Okay, now I just add the data. For example, initial, this is not important. Transferring number of lithium is 0.36. Okay, electrolyte conductivity. I don't know. Electrolyte capacity ampere h divide by g. I don't understand what g it means here. It means gram. It's so weird. I don't know. Really, I don't know. I add this transferring number, reaction rate. It was added before. Electrode area density. Oh, it is density. Oh, what is that? And I don't know where is that. Electrode solid content 100% is okay to inject capacity. Oh, we define capacity here by ampere hour, and we define IC and JC by this formula. We can define IC or JC here. Okay. Where is diffusion coefficient? I don't know. The Faraday constant, it doesn't matter this value or this value, maybe. Okay, these are for thermal model. That is not our concern for now, because maybe this video will have two parts. This is the second part. This is the first part, excuse me. and heat capacity, density, thermal conductivity. I don't know. This is for thermal part. I will continue. We have capacity, battery dimension. Oh, I don't know. There is no talk about diffusion coefficient. I don't know. There is nothing. But I just have some parameters I added from example. Just uh, for examining. Okay, then we can just search in the reference of that paper to find what is the exact value for the simulation. Okay. Or maybe we could find from materials. Let me. Maybe we can add from material library. Just let me search it. Find some material. For example, for battery, we have some electrodes or electrolytes. We can choose LiPF6, for example. I don't know. Let me check in the paper. LiP, F, IP. Oh, nothing. Oh, they must talk about it. I don't know. I don't know why they don't talk about it. Just they said that it's separator. Nothing more. Let me check the electrode. We have graphite, silicon, LMO, LINO, NMC, or oh, I see that. Let me check. NCM. Okay, NCM, it's cathode. NCM. What? Here is NCM, but here is NCM, and Okay. It is so weird. Here it's NCM, but I see here is NMC. NMC, what? Here we have NMC 111. Let me check. NCM, nothing more. MCMB. We have MCMB. I saw that. Where is it? Here we have MCMB, and there is nothing. Lumped. Let me. Okay. We have MCMB. I added. It must be MCMB. It must be negative or anode. I just copy anode name and disable this, and I add this as anode. Or we can, let me Control X, anode. Here I add the and the parenthesis. Okay, I add this as anode, and anode is here. Okay, why it is not SOC? Oh, it must be. You must add SOC. Let me check the. I'll be corrected, but at first let me add the material anode, and for cathode we have NCM cathode. Yes, it's negative, it's okay, and positive, it's positive, yes, NMC. So weird. NMC, and it is not correct. NCM, we can check it. Okay, it is look at this is NCM, but we see here NMC. It's okay. NMC, I don't know which one, but we can use one of them. I choose 111. Okay, I choose this one, for example, and it will be cathode. And for the I choose this as liquid ion battery. Okay, it will be a separator or electrolyte. I disable this, I choose separator. I write also electrolyte. Nice. And it must be electrolyte. NMC, it must be cathode. It must be cathode, okay. And also this must be anode, okay. I can remove this tree. I cathode here, separator, foil, cathode, separator on it, and I just say it. Okay. Here also I check it. It is electrolyte. Okay. In cathode we don't have. I can define it, for example, the conductivity. Oh, I have some parameters here. Let me define the cathode. Sigma. Okay, let me check this one again. It must be separator, and also for this it must be separator. Oh, now it is all of them, it's defined. Okay, very nice. But here we can see maybe SOC can be defined. Let me check these values. SOC here. Okay. Maybe we must define this value SOC, where we can define it. I'm just searching for that. I really don't know. Here we have SOC. I don't know why it couldn't be for anode. Choose electrolyte properties. Sigma S is 10. Isotropy. But for anode, isotropy, it is the same, but I don't know for anode why we have different. SOC from material cubic. You can add heat of mixing, but I don't want to add it here now. Extrapolation SOC. This is the same extrapolation. Cross particle from material. For cathode it is okay. Int 1 SOC. But for anode it is not okay. T-ref. I don't know. This is local variable that not variable T. Oh, it I understand what is that. It may be can be added by multiphysics with heat transfer solid, maybe, because these are all temperature dependent, and maybe, but by adding the temperature it can be added in another component, but not for here. Okay. We must add another component. And in that component, we can add temperature Here we can add, go to home, add another 3D component. In that new component, we must add this geometry, and then after defining this geometry, we can couple them. Here, let me show you. For example, I go to physics, I add physics, choose heat transfer. I choose heat transfer in solid and fluid because we have solid and fluid, both of them. I group by a space dimension. We can add, we have fluids, solids. We can add two solids, for example. And here we can add, for example, thermoelastic damping, irreversible transformation, optically thick participating medium, phase change material. For example, irreversible transformation, we can see the Q is equal to rho L rho T. That maybe we can add these equations. We can work on all of them. We must work on them, but not for now, because our tutorial was very heavy for now, and we can okay. And here we can add overheating, overcooling analysis, or a specify material domain for that, or thermoelastic damping, QT. I see that. I think we have 1, 2, 3, 4 terms of Q. That is, we have Q irreversible and reversible. The irreversible is contain O, ACT, and EXT. ACT may be for polarization heat. Let me see. The irreversible heat involved the ohmic heat and polarization heat. The transportation of charge in solid conductor and actually causes ohmic heat. Transportation of charge, ohmic heat. Maybe ACT, or we can add them. These are all of them are Q. QTD, it's maybe thermoelastic. When we add any Q, let me disable this. I guess still see that. Optically thick. From absorption and scattering also, this is not our concern here. But we can write this code for any equation. Maybe these are must be come from the equation of electroanalysis in part 1, electrochemical model. This Q, reversible ohmic act, can be calculated by the first part by coupling, and we can write them by writing codes. Let me check flight properties. Okay. Okay, we must write the code to adding them. We could add heat mixing here. Here we can add heat mixing. When we add heat of mixing, it can help us for some variable defining. Let me. Okay, maybe till here it is okay for now. It was about 4 hours, I think, but we can continue this model in the second or third part, and we'll continue to simulate completely. Okay, but for now I think it is enough for now. Then we will continue this simulation and this work. Okay, I hope you enjoyed this video. This video is the first part of the simulation. Please subscribe to my channel, share my channel to your friend. You can support me by super thanks, or if you have any project, you can text me on WhatsApp or email to me, and just support me. Share my channel to your friends, like my videos, see all of them. Please don't download them, just see them, because the field of my YouTube is so hard, and nobody produce videos like that, and I try to do my best to have a good and best videos for your research that very help you. This is not just for a specific field. When you see these videos, uh, you will learn anything, and you can use these ideas to your project. Okay, have a good time, take care, goodbye.